Okay, let's start the next part of the video, which is about the types of hybridization. We'll go through the types of the hybridization and I'll explain each of the types with 3 to 4 examples. And we will also discuss the structure of ethene. As in the previous video, I've explained the structure of CH4 and explained why hybridization theory was needed and why VBT was rejected. Here, I'm going to explain the types of hybridization, which are the Sp hybridization, Sp3 hybridization, Sp2 hybridization. In the first part, I'll explain the first 3 Sp3, Sp2, and Sp. Starting from the Sp3 hybridization. So the basic definition of Sp3 hybridization is depicted from the name Sp3, which means that 1s and 3p orbitals intermix to form 4 equivalent Sp3 hybrid orbitals. As I have discussed before, parent orbitals mix up, intermix, and then make new orbitals which have same energy and same characteristics. Here in Sp3 hybridization, 1s and 3p orbitals will intermix. An important point I would like to discuss here is that only the central atom takes part in the hybridization process, and then it overlaps with the other orbitals and other atoms to form molecules. From the example of NH3, as I have discussed before the CH4 in the previous video, I'm going to discuss NH3 ammonia structure here. The electronic configuration of nitrogen in the ground state is 1s2, 2s2, and 2p3. Talking about the valence shell electronic configuration, in the ground state it is 2s2 and 2p3. Hybridization occurs in the last orbitals of the valence shell electrons, and an electron jumps into the p orbital, forming 4 sp3 orbitals. This is an example of sp3 hybridization. That's why 2s1 orbital will combine with 3p orbitals, which are named as 2px, 2py, and 2pz. And they will combine to become a hybridized orbital named as sp3. These 4 orbitals will have same shapes and same energies, but the orientations will be different, and the orientation will be such that the stability of the molecule is maximum. Now, taking a look at the orientation, I'll explain you what orientation means. Here I'm going to draw an s orbital. Consider an s orbital combined with a 2px orbital, which is in the x-axis, and a 2py orbital, which is in the y-axis, and a 2pz orbital, which is in the z-axis. As we're discussing sp3 hybridization, I'll tell you how these 4 hybridized orbitals will form after the combination of 2s, 2px, 2py, and 2pz. Now, if we're talking about ammonia, the overlap forming in ammonia molecule is the sp3s overlap. After the hybridization in the central atom, it will combine with the s orbitals of hydrogen. As hydrogen has only 1 electron, it has only s orbital. So the circles are for the s orbitals of hydrogen, and the lobes, as I talked about in the previous video, the lobes are for the sp3 hybridized orbital. Only 3 of the hybridized orbital will take part in the combination with the hydrogen's s orbital, because NH3 has only 3 molecules of hydrogen, and the other lobe will have a lone pair of electrons. The geometry of the lobes changes, the orientation of the sp3 hybridized orbitals changes, and there is a bond angle of 107.5 degree. So here, for the clearance of the concepts, as we know, there is an s orbital and 3 p orbitals, as in CH4. The very next example is about the H2O molecule. As we know, H2O molecule is a common molecule. We know it is formed from 1 atom of oxygen and 2 atoms of hydrogen. Focusing on the ground state electronic configuration of the central atom, which is the oxygen, we know that the valency or the valence shell electronic configuration of oxygen is 2s2 and 2p4. That means the s orbital in the valence shell has 2 electrons, the 2px has 2 electrons, and 2py and 2pz have 1 and 1 electron. So we're talking about the sp3 hybridization, so the combination of one s orbital and the 3 p orbitals will form sp3 hybridized orbitals, which are 4 in number. As we know, oxygen has 2 pair of lone pair electrons. So here is the structure of oxygen and the orientation of the lobes. So here the oxygen has 4 sp3 orbitals. 2 of them will combine with the s orbital of hydrogen, and there will be an sp3 s overlap because sp3 is combining with the s hydrogen. There is an overlapping here. Repeating my point, sp3 hybridization occurs only in the central atom of oxygen in this case, and then the sp3, 2 of the sp3 hybridized orbital will overlap with the hydrogen s orbital. Heading towards the second type of hybridization, which is the sp2 hybridization. From the name, we got to know that sp2 hybridization means that there is one s and 2p. Let's get to the definition. The hybridization which has only one s and 2p orbitals, where one s and 2p orbitals intermix to form 3 hybridized sp2 orbitals. As I told before, orbitals are named after the parent orbitals, so sp2, and the quantity or the number of the orbitals will be 3 because there is one s and 2. Taking the example of BF3, Boron Trifluoride, the ground state electronic configuration of the middle or the central atom B is 2s2 2p1. So the ground state electronic configuration in the form of the electrons will be this. When boron has an excited state, the electron from the 2s, one electron from the 2s jumps into the 2py orbital as it is vacant. Here I have demonstrated the excitation process for your clearance of the concept, that how the excited state in boron happens, and the resulting hybridized orbitals will be sp2 orbitals, and they will be 3 in number. So while talking about boron trifluoride, the central atom boron is hybridized. Its orbitals are hybridized, intermixed, and the 2s combined with the 2 of the p orbitals, and it gives hybridized orbitals which are named as sp2 orbitals. There are 3 hybridized orbitals formed after the hybridization of boron. After the hybridization of boron, boron overlaps with fluoride molecules, fluoride orbitals, and forms a BF3 molecule. This is how it's going to happen. So one of the p orbitals of F is half-filled, which is 2pz. This is in the form of a lobe, and the lobe overlaps with the sp2 orbitals of boron. 3 sp2 orbitals overlap with the lobe-shaped p orbitals of 3 fluorine atoms individually. The structure is, I'm going to draw the structure now. That will help you to understand the structure of boron trifluoride. The bond angle will be 120 degree. And here we need to understand that 1s is combined with 2p orbitals in the central atom of BF3, which is the boron. And after the hybridization of the orbitals of the boron, after the intermixing of boron orbitals which are hybridized then overlap with the fluoride orbital. So basically, hybridization occurs in the boron molecule and then it overlaps with the other orbitals of other molecules to form chemical bonding between those molecules, like in the case of BF3. Here I'm going to draw the structure. Now you'll get a good explanation about that. The bond angle is 120. The shape is... Here I'm demonstrating the f orbitals, the electrons in the f orbitals, and these f orbitals will combine with the boron hybridized orbitals, giving an sp3s overlap. So we got to know that 1s and 2p orbitals. From the case of BF3, we got to know that 1s and 2p orbitals will combine to form sp2 hybridized orbitals, which are 3 in number because there is 1s and 2p. Always remember that. Another great example in which sp2 hybridization is observed is the structure of ethene. Again, electronic configuration of carbon is needed here because the hybridization will occur in the carbon atom, and then there will be overlapping between the carbon orbitals and carbon 2 carbon atoms. So we will see how this happens. The ground state electronic configuration of carbon is 1s2, 2s2, 2p2, which means in the excited state, one electron will jump into the orbital which is awakened, and then the hybridized state will come. So, one electron from the 2s2, like in the BF3, there was sp3p overlap. Same is the case here. Here, carbon is required, and the carbon in the excited state has an electron which is jumping into the awakened orbital, and then here sp2 hybridization will occur. In the first example of CH4, we had an sp3 hybridization occurring, but here only one s and 2p orbitals will intermix and 3 sp2 orbitals will form. As you can see, you might be thinking that like CH4 there will be 4 orbitals, but for your information here, only 2 p orbitals and 1 s will combine, intermix. That is why only 3 orbitals will form. Sp2 hybridization occurs here because the ethene structure requires sp2 hybridization. In the formation of ethene, carbon will undergo sp2 hybridization and 3 hybrid orbitals will form, which means 1s plus 2p is equal to 3 sp2 orbitals. Well, I'm going to draw the structure now, and I'll explain how CH2 and CH2 has a double bond and has overlapping, which is the sp2s overlapping, and what is the structure of ethene. So here we have a carbon atom which has sp2 hybridized orbitals. 2 of the sp2 hybridized orbitals will overlap with the hydrogen s orbital, which will overlap like sp2 and s overlap, and the other carbon atom has the same thing. 2 sp2 orbitals will overlap with hydrogen, and the other one sp2 will not overlap with hydrogen's s orbital. Now, after the formation of the overlaps between hydrogen atom and the sp2 orbitals of carbon, the middle sp2 and sp2 orbitals will combine and overlap, First, there is a sigma bond formation, and then there are two orbitals combining, which will form two pi bonds. Heading towards the third type of hybridization, which is the Sp hybridization. As the name says, Sp, that means only one S and one P. So, let's understand this hybridization. In this hybridization, one S orbital and only one P orbital intermix. Here, the parent orbitals are 1s and 1p, only two parents. The two of them will combine and intermix to form an sp hybridized orbital. And the number of hybridized orbital depends upon the parent orbitals, which is 2. So 2 hybridized orbitals will form after the combination of s and p orbitals of the single atom. To understand this sp hybridization, I have an example of beryllium chloride. The ground state electronic configuration of beryllium is 2s2 and 2p0. So in the excited state, beryllium, as it has 4 atomic number, the electron from 2s will jump into the 2px, thus forming 2 of the hybridized orbitals, which are the sp hybridized orbitals. So this hybridization causes the structure of beryllium chloride. When beryllium has hybridization in it, then its hybridized orbital will overlap with chlorine atoms, with the orbitals of chlorine. So it has a bond angle of 180 degrees because the orbitals are in themselves such that the repulsion is at the minimum. So beryllium sp orbitals will overlap with the chloride orbitals, which is the p orbital. So there is an sp-p overlap. Beryllium, once again I'm repeating this, beryllium has hybridization and then it overlaps with the p orbitals of chlorine. That means the hybridization explained here is that 1s plus 1p combines to form a hybridized orbitals, which is the sp2 sp orbitals. This hybridization is also seen in ethene. To understand this, we need to know the electronic configuration of carbon. As we know, the ground state electronic configuration of carbon atom is 2s2 and 2p2. So an electron from the 2s will jump into the 2pz, and the carbon atom will enter the excited state. And after the intermixing of these orbitals, there will be sp hybridization, and 2 of the hybridized orbitals will form, which are the sp-sp orbitals. So we got to know that carbon shows multiple types of hybridization, like sp3 in CH4, sp2 in ethene, and sp in ethene. This is due to the structural differences between ethene and ethene in CH4. So, understanding the bond, there are 2 sp hybridized orbitals and 2 unhybrid orbitals. In the formation of ethene, there is a triple bond between carbon and carbon and overlapping between hydrogen. The sp hybridization explains ethene such as there is an sps overlap between one hydrogen atom and one hydrogen orbital and orbital of one hydrogen and sp orbital of carbon. In the carbon-2 atom, the same thing occurs. There is an overlap between the sp orbital of carbon and the s orbital of hydrogen. Now the leftovers are the sp orbitals in one carbon and the sp orbital in the second. As we can see clearly that sp left orbitals overlap with each other between the two carbon atoms, and the other sp ones overlap with the s orbital of the hydrogen. Thus, it makes a sigma bond, and the other two orbitals overlap to form a pi bond. Hybridization has no link with the pi bond. Pi bond is just an overlapping. Pi bond means parallel or side-to-side overlapping of atomic orbitals, and hybridization is something else. Hybridization means intermixing of atomic orbitals. So let's start the summary of these types of hybridization: sp3, sp2, and sp. Starting with the number of hybrid orbitals. So the sp3 orbital has 4 hybrid orbitals and 0 non-hybrid orbitals. And the molecular geometry is tetrahedral, as we saw in NH3. The S and the P character is, as there is one S orbital and P, there are 3 P orbitals, so the S character is 25% and 75% is the P character. In the sp2 hybridization, 3 is the number of hybrid orbitals and 1 is the non-hybrid orbital in the case of carbon. Mostly. The molecular geometry is triangular mostly, and the S character is 33% and 66% is the P character. The sp orbital, the sp3 hybridization has hybrid orbitals, which is the sp orbital. It has 2 hybrid sp orbitals. And if sp hybridization is occurring, then there are 2 non-hybrid orbitals in the case of carbon. The molecular geometry in the case of carbon is mostly linear, and the S character is 50% and P character is also 50% because there is one P and one S orbital mixing. This summary is also a general summary about sp3, sp2, and sp hybridization. In the next part of the video, we will start the sp3d, sp3d2, and sp3d3 hybridization. Thanks for watching.